Hello everyone, welcome to my video on the properties of definite integrals. So we'll begin by stating the properties, we're going to prove them, and then we'll look at a couple of examples and apply the properties. So the first one that we have, we actually seen already. Let's go ahead and take a look. It's the fact that the integral from a to b, so it's a definite integral, it's defined at the bounds, of a constant c dx, so we're integrating with respect to x, is equal to c times b minus a for all c in R. So let's go ahead and prove this statement. What's the proof? We'll do it using a sketch, just to get the idea. How do we get from this to this? Well, this is saying you're working with the function c. So if I graph this, and let me do it in green, c is a constant, and we're taking the area under the curve from a to b. So we're starting at some value a, we're starting at some value b. C doesn't necessarily have to be positive. Right now I have it drawn on a positive case, but you could consider C on the negative side on the y-axis, let's say, and you get the same argument. So if C is positive or negative, it doesn't change the argument that we're making. So C is a constant from A to B, so it's essentially just a straight line. It's supposed to be a straight line. Okay. And you can see right away that this gives us the area of a rectangle. Okay, and how do we find the area of a rectangle? This region here, A. Well, to find the area of this rectangle, what you're going to do is A equals length times width. Well, what's the width? Let's call the base here the width. To find this distance, you're simply going to subtract B from A. So we get B minus A. And then what's the height of the rectangle? Well, that's simply just C. So you're multiplying by C. And that gives us this result here. So it comes just from the sketch, okay? If C was negative, you would just get a negative area. It's okay because we're talking about net area when we're talking about the definite integral. So this statement here holds, okay? From the fact that this is just the area under the curve, which in this case, when you're dealing with constants, we know we get rectangles, okay? So this one here is done. Let's look at the next property. So in this next property over here, we have the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b plus or minus the integral from a to b of g of x dx. So what this is saying is if you have an addition or a subtraction of two functions, then you could essentially take the integral of each term individually. Or in other words, the integral of the sum is equal to the sum of the integrals, or the difference, the integral of the difference of two functions is equal to the difference of the integral of those two functions. Okay, so we've seen this with limits, we've seen this with derivatives, so the same idea holds. Let's go ahead and prove this. So the proof is, let's begin with the integral of a to b of f of x g of x plus or minus g of x. We'll do the sum and the difference at the same time. And by definition, we know that this is equal to the limit as n goes to infinity of the summation from 1 to n of f of xi plus or minus g of xi. All this in bracket and times delta x. Okay, so this is just by definition. Next, what we could do is distribute the delta x to each term, giving us the limit as n goes to infinity of the summation I equals 1 to n of f of xi times delta x plus or minus g of xi times delta x. And now I'm going to do this next step, two steps in one, where we essentially argue that whenever you're taking the sum of two terms, you could take the sum of each term individually. And similarly for limits, whenever you're taking the limit of two terms, which are being added or subtracted, then you can take the limit of each term individually. So what I have, because technically right now what we have is all this is in brackets, it's inside the limit and the sum. We're just going to take the limit and the sum of each term individually, which we've seen in earlier videos. This is properties that we're allowed to do. So we have the limit as n goes to infinity, summation I equals 1 to n of f of xi times delta x plus or minus the limit as n goes to infinity, the summation from 1 to n of g of xi times delta x. Okay. And by definition, this is the integral of f, a to b, dx, plus or minus, and this is the integral of g from a to b. And we're done. This is what we wanted to show. Okay. So let's look at the next property. So property 3 states that if we have the integral from a to b of c times a function, dx, integrating with respect to x, that's equal to the constant. We can essentially take the constant and pull it out and deal with the integral on its own from a to b of fx dx. Okay, so we've seen this idea with limits, with summations, we've seen it with derivatives, and it works also with integrals, which is great. And c is just a constant, so for c and r. Let's go ahead and prove this. The argument stands from, again, we begin with this statement and we apply the definition. So the integral, let's write the proof. The integral from a to b of c times f of x dx, by definition, is equal to the limit as n goes to infinity of the sum from I equals 1 to n of c times f of x I times delta x. Okay. If you want, you could put xi star because you could be working with sample points. It doesn't really matter. I'm just going to state it as f of xi. And again, c comes out of the sum, which we know we're allowed to do. We saw that in our summation video. And we know c could be removed from the limit because it doesn't have any n. And for the sum, it doesn't have any I. C is just a constant. We remove them twice. So instead of doing it in one step each time, I'm just going to pull it out right away. Okay, so c comes on the outside of the sum, then it comes out again from the limit, putting it in the front, leaving us with c times the limit as n goes to infinity times the sum from 1 to n of f of xi times delta x. And again, this piece here is just our definition for the integral of f. So we get c times the integral from a to b of f of x dx. And we're done. This is what we wanted to show, okay, for any constant c. Okay, so this is a nice property. We know if we're dealing with constants, we just remove it, ignore it, and integrate the function on its own. Let's move on to the next property. So the next property states that if you have the integral from a to a of f of x dx, it's equal to 0. So if the bounds of integration are the same value, it's equal to 0. Pause the video, try to prove this. I think the proof is fairly easy. If you try sketching it, you should have an intuition that that does make sense. If you have some function and you're starting at a and you're finishing at a, well, the width of the rectangle that you're sketching or the area under the curve is going to be 0. And this is basically the idea. Okay, but without the sketch, let's go ahead and prove this. So I'm going to begin by stating the definition. So we know by definition this thing here, the integral from a to a of f of x dx is equal to the limit as n goes to infinity of the summation I equals 1 to n of f of xi, or xi star, doesn't matter, times delta x. Okay. How do we prove that this thing's equal to 0? Well, we could take a closer look at delta x. What's delta x equal to? We know that delta x is equal to b minus a over n. But in this specific case, our lower bound is a, but our upper bound is not b, it's a. So here, what we really have is a minus a over n, which is equal to 0 over n, which is 0. So delta x is equal to 0. So the limit as n goes to infinity of the summation I equals 1 to n of f of xi times 0, this piece here is 0. And you're summing up a bunch of zeros, which means that the limit is equal to 0, and this is the proof. We're done. Okay. So this is very tricky. You have to be careful with the bounds of integration. If they're the same, whatever function they give us, they could give us something that we can't even integrate. It doesn't matter. If the bounds are equal, the answer is just simply 0. Okay, so be careful for that trick. Let's look at the next property. So the next property over here, property number 5, we have the integral from a to b of f of x dx, and that's equal to negative of the integral. Instead of a to b, now we're going from b to a of f of x dx. So essentially, if you flip the bounds, a negative comes out. Let's go ahead and prove this. So I think it's easier to start with the right hand side. So we'll start with the right hand side and try to prove and get to the left hand side. So proof, we have the negative integral of a to b, sorry, not a to b, b to a of f of x dx. This is equal to negative, I'm going to keep the negative in the front, and the integral from b to a is the limit, by definition, the limit as n goes to infinity, summation I equals 1 to n, f of xi times delta x. Okay, but what's delta x? Well, delta x, we know, is equal to b minus a over n. Or, in a sense, we know it's the upper bound minus the lower bound. Okay, so don't get attached to the letters. Here it's actually reversed. So what we have for delta x, in our specific case, it's the upper bound minus the lower bound divided by n. So what we have is a minus b over n in this case. Okay. So we have negative ln, negative limit as n tends to infinity, summation from 1 to n, f of xi times delta x, which in this case here, delta x is a minus b over n. But if we distribute the negative, so the negative is a constant, we jump into the limit, we jump into the sum, and we multiply this term by negative 1, get treated like a constant, we get the limit as n goes to infinity, summation I equals 1 to n, f of xi times b minus a over n. Right? So if we multiply this by negative 1, we get negative a, positive b. So I just reversed the order to put it in this form, which is the way we like it. And this we know is back to our regular delta x. So this gives us limit as n goes to infinity of the summation from 1 to n of f of xi times just regular delta x. So we're back to our original integral from a to b of the function f of x dx. And this is the proof. This is what we wanted to show. So we just went in the reverse order, but we showed negative of the integral from b to a of f of x dx. When we brought them back, a is now on the lower bound, b is on the upper bound. Now it's positive, okay? So just remember, if you flip the bounds of integration, you have to switch the sign, okay? It turns into a negative. Okay. So let's take a look at our final property. So our final property that we have here, property 6, is the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. So essentially, if the upper bound of the first integral matches the lower bound of the second integral, and you're adding the two integrals, well, you could just jump straight from the lower bound of the first one to the upper bound of the second one. And this has to be the same function for this to work. Okay, so essentially if these two match, then you could go straight from A to C. Okay, the proof for this is a bit difficult, so I'm going to skip it. I'll let you guys work on it if you want to try it. You're just essentially considering different cases. But let me give you the general idea. So the idea to convince you of this property is, if we consider the sketch, we have this is our y, this is our x. We begin at some A. We'll take b to be over here, and we have c to be over here. It doesn't necessarily have to be in this order. I mean, b could be smaller than a. You could rearrange this. But for the sake of simplicity, let's just let a be the smallest value, c the largest, and b in between. And let's consider, I don't know, some function from here to here. All this is saying, let's do b in red. If you take the integral from a to b of f of x, that integral represents area 1, which is just this, the area under the curve, this region here. So we're integrating from a to b, this function here, the green function is f of x. So if we integrate from a to b, it gives us this area here, and if we integrate from b to c, that gives us area 2, so plus area 2, which is this region. So if we add these two areas, we get the entire area from a to c, the whole thing, a total, right? That's all it's saying, so it makes sense. But proving it's a bit more difficult, but this is the idea. So instead of integrating from a to b, this piece, and then continuing from this piece to this piece, you could just take the integral one shot from a to c. Okay, so these are the properties. Let's go ahead and apply them with a couple of practice problems. So in this first example over here, it says if the integral from 1 to 5 of f of x dx is 10, and the integral from 4 to 5 of f of x dx is 4, then find the integral from 1 to 4 of f of x dx. Okay, so let's go ahead and take a look at a sketch, because hopefully this could simplify the problem for us, or give us a better intuition of what we expect the answer to be. So I don't know what the function f of x looks like, but let's go ahead and just sketch some function. And we're going to sketch it from 1 to 5. So let's say it's here, it goes to here. This x value here is 1. This is 5. And let's put 4 over here. So the first bit of information that's given is that the area from 1 to 5 is 10. So the whole thing, the entire area is 10. And it tells us the area from 4 to 5 is 4. So the area underneath the curve from 4 to 5, this area here is 4. And we know that the whole thing, the area under the curve, is 10. What would you expect the area from 1 to 4 to be? Well, what do we have to add here to get an entire answer of 10? The answer is simply 6. Okay, so this is the idea, because 4 plus 6 gives us 10. Okay, but let's prove this mathematically. Let's use our properties to prove this. But this is based off the graph. We should have an intuition of what we expect the answer to be. But let's go ahead and solve it. So we want to build to go get 1 to 4. How do we do that? Well, we have to use property 6. We want to add this function with this one. So we're starting at 1 and we want to finish at 4. But the issue here is that the 4 is on the bottom. We know if the upper bound of 1 matches the lower bound of the other, then we could connect them using property 6. But in this case, it doesn't work because 5's on top. We want one of these 5s to match. Since the lower bound that we want is 1, and here it's already 1, we want the upper bound here to be 4. How can we put the 4 on the top? Well, this comes to the property where we could flip it and put a negative in the front. Let's go ahead and do that. So we know the integral from 1 to 4 f of x dx can be expressed as the integral from 1 to 5 of f of x dx plus the integral from 5 to 4 of f of x dx. This is property 6. The fact that the upper bound here matches this one, we know this statement to be true. Okay, even though 5 is larger than 4, it doesn't matter. This value here could have been any value. It could even be negative. Doesn't matter. But now we broke it up into two terms that we know. The only well, this one here we know. The only issue is this: we have 5 on the bottom, 4 on the top. What do? We're just gonna flip the bounds. So this is the integral from 1 to 5 f of x dx. And if we flip the bounds, we switch the sign. So it's positive. We put a minus. Now we go from 4 to 5 f of x dx. We know the integral from 1 to 5 is 10, minus the integral from 4 to 5 is minus 4, and that gives us an answer of 6, as we expected, so 6 units squared. Okay, because we're talking about area. Okay, so this is an example of using properties. Let's take a look at a harder example. So example 2 here, it says if the integral from 0 to 3 of f of x dx is equal to negative 1, and the integral from 0 to 3 of g of x dx is equal to 2, then find the integral from 0 to 3 of 4 times f of x plus 3 times g of x dx. Okay, so pause the video, try to do this on your own, see if you're able to get the answer. So here we just use our properties. First of all, this is the integral of a sum. We could express this as the sum of two integrals. 0 to 3 of 4 f of x dx plus integral from 0 to 3 of 3 times g of x dx. Okay, so we separate it, we take the integral of each term individually, and now we're using the other property where we have a constant in front. Whenever you're dealing with a constant, we could simply just remove it from the integral in both cases. So let's go ahead and do that, leaving us with 4 times the integral from 0 to 3 of f of x dx plus 3 times the integral from 0 to 3 of g of x dx. Okay. This we know the answer, and this we know the answer. We know the integral of f of x from 0 to 3 is equal to negative 1, and the integral from 0 to 3 of g of x dx is equal to 2. So we're done. This is 4 times negative 1 plus 3 times 2. Negative 4 plus 6 gives us 2 units squared. And that's the final answer. Okay, so I hope you got that. Not too bad of a problem. Let's take a look at a harder problem now. So in the next example, we have to express the following as a single integral of the integral from a to b of f of x or g of x dx. So express this as one single integral. In this case, we have 4 of them. So we have the integral from negative 7 to negative 3 of g of x dx minus the integral from negative 1 to negative 4 of g of x dx minus the integral from negative 2 to negative 2 of g of x dx, and then minus the integral from negative 4 to negative 3 of g of x dx. So let's go ahead and solve this. There's different ways of doing this, but the way I see it is to first, I'm tempted to factor out all these negatives. So this is equal to negative 7 minus 3 g of x dx minus, in brackets, the integral from negative 1 to negative 4 g of x dx. Before I continue, this one here, everyone should know the answer to this. What's the integral from negative 2 to negative 2 of g of x dx? Don't fall for this trap. The bounds of integration are the same, so the answer is just simply 0. So this guy's gone. Okay, so this is 0. So I'm not going to include it. And then we're going to have this last term, which now that I factor out the negative, it became a plus, and it's the integral from negative 4 to negative 3 g of x dx. Okay, so we simplified it to 3, so from 4 down to 3. Let's combine the 2 in the brackets. We could do this because we know that the upper bound matches the lower bound, so this is property 6. So we could take this straight from negative 1 to negative 3, canceling out the negative 4. So this gives us the integral from negative 7 to negative 3 of g of x dx. We have a minus on the outside, and then we have the integral from negative 1, we're going from here to the upper bound, to negative 3 of g of x dx. Okay, so we're almost there. Now we have to compare these two. We reduced it down to 2 integrals. Now we use the property that if we have a negative, it flips, because again, we want to apply property 6, where one of these bounds matches these ones. But notice that here we have a negative 7, the upper bound's a negative 3, so we want the negative 3 on the bottom. So to do that, we're going to flip the bounds of integration. So negative 7 to negative 3 of g of x dx. The negative turns into a plus because when we flip the bounds of integration, the sign switches, so negative turns into a plus. And now we have negative 3 to negative 1 g of x dx. And then we ended off with property 6, where the upper bound matches the lower bound, so we could go from the lower bound to negative 7 straight to the upper bound negative 1. And that's the final answer. We have the integral from negative 7 to negative 1 of g of x dx, and we reduced it down to a single integral. Okay. Let's look at the next example. So in this next example over here, it says to suppose that the integral from negative 1 to 3 of f of x dx is 5, the integral from negative 2 to negative 1 of f of x dx is 3, and the integral from negative 2 to 3 of g of x dx is equal to 4. Using that information, find the integral from 3 to negative 2 of 2 times f of x minus 6 times g of x. Okay, so pause the video, give this a shot, see if you're able to solve for the answer. So the first thing I'm going to do is separate and take the integral of each term individually. And at the same time, I'm going to factor out the constants. Okay, so we have 2 times the integral of 3 to negative 2 of f of x dx minus 6 times the integral from 3 to negative 2 of g of x dx. Okay, so the issue here is that we have to break this up into the information that's given. So we want to go from 3 to negative 2. So what we could catch is that here, since the upper bound and the lower bound match, from negative 1 to negative 1, we know the answer from negative 2 to 3 of f of x, taking the integral from negative 2 to 3 of f of x, is equal to 8. Okay, so let's go ahead and separate this. So what we get is 2 open bracket. The 3 and the negative 2 will separate it to get a negative 1 using property 6. So this is equal to 3 to negative 1 f of x dx plus negative 1 to negative 2 f of x dx. Okay, both these terms are multiplied by 2. And then we have minus 6 times here. Well, we could solve this right away because we want -2 to 3. We have 3 to -2. It's the opposite way. We're going to flip it. But in doing so, by flipping it, it turns this into a plus. So we get plus 6 integral from -2 to 3 of g of x dx. This piece here is okay. This is done. We have it. The integral from -2 to 3 of g of x dx is just 4. So we have 4 over here. Now we have to go use the same idea on the function f. So here we have 3 to -1. We want to flip it, so this is going to become negative, giving us 2 times -1 to 3 of f of x dx. Yeah. Minus, and again, this one we want to flip as well because we want -2 to -1. So we put a minus, -2 to -1 f of x dx plus 6 times 4. Here what we get is 2 times negative, this is 5. Okay, we have 20 brackets. We have -5 minus, here this is equal to 3. 6 times 4 is 24. -5 minus 8 is minus 3 is -8, giving us -16 plus 24. So minus 8 times 2 is -16 plus 24, giving us a value of positive 8 units. And that's the final answer. Okay. So this is using property 6. Property 6 shows up often. Property 6, the one where we have to flip, I don't remember the number I used. That one, and pulling out the constant. Those are very common properties that we use for these types of problems. So let's look at our final example. So exercise 5, it's telling us to prove that the integral from a to b of 1 dx is equal to b minus a. So this is a very simple proof because we know we have the property that the integral from a to b of any constant is equal to that constant times b minus a. Well, in this case here, the constant is just 1. So the integral from a to b of 1 dx is equal to 1 times b minus a, which is b minus a. And we're done. This is the proof for the simple case for the integral from a to b of 1 dx. Let's look at part b, where we look at x now, the integral from a to b of x, and we're going to go ahead and prove that. So part b over here, it's asking us to prove the integral from a to b of x dx and show that that's equal to b squared minus a squared, all that divided by 2. Let's go ahead and do this. This one's a lot more difficult because we don't have our property. We have to use our limit definition. So let's rewrite this as the integral from a to b x dx, and using the limit definition, limit as n goes to infinity of the summation I equals 1 to n of, it's really f of x I times delta x. I guess we could write it this way just to show our work. Let's go find our xi and our delta x. Delta x we know is b minus a over n, so that's what we have, b minus a over n, and xi we know is a plus I delta x. And in this case, our delta x is b minus a over n. Okay. So we have our xi, we have our delta x. So xi, we're just taking this function and plugging it into this one here, which is just x. It's the identity function, so we're just left with, so f of xi is just simply this, leaving us with the limit as n goes to infinity, summation I equals 1 to n. F of xi, as I just stated, xi is this, f of xi gives us back x, so we're just left with a plus I times b minus a over n, and then delta x on the outside is simply just b minus a over n. Okay. So let's go ahead and find the sum. We could begin by distributing the b minus a over n on both terms, giving us the limit as n goes to infinity, summation I equals 1 to n. We get a times b minus a over n. So multiplying this by the first term, and now we're going to multiply this by the second term, giving us I times b minus a over n, all this squared. Same thing. So we get b minus a, all that over n squared. And now we're going to deal with each term individually. We're taking the sum of each term. This here has no I, so it's just a constant. We could pull it out of the sum, giving us the limit as n goes to infinity ab minus a over n. There's no i's involved, so the sum from I equals 1 to n is just a constant 1. We know this, we have a property for this. Plus, let's take the sum. The second term over here, I'm going to pull out the b minus a over n squared because it doesn't have an I, and leave just the I inside the sum. So we get b minus a squared over n squared times the sum I equals 1 to n of just I. Which again, this, we have a property, we know this. So I'm going to have to erase, give myself a bit more room. Let's move this out. So this continuing up here, we get the limit as n goes to infinity, a b minus a over n. And we know the summation from 1 to n of just 1 is n, because we multiply the constant times the upper bound, or the n in this case. So 1 times n is n, plus b minus a squared over n squared times the sum of I, we know from our rules, is n times n plus 1 over 2. So let's go ahead and solve this. So here we're taking the limit, so the n's essentially cancel, leaving us with just a times b minus a. So this part is done. Because the limit is as n goes to infinity, the n's canceled, leaving us with just this term. Since there's no n's, the fact that n is going to infinity doesn't affect our constant here. But now we have to take the limit of this term. So we have plus the limit as n goes to infinity of, on the top we have b minus a squared, and that's multiplying this term here. But n times n plus 1 is really, if we multiply the n, is n squared plus n. And again, we just look at the highest exponents of the numerator and denominator. Since the highest exponent on the denominator is 2 and on the numerator is 2, we ignore this n and we take the coefficients of both these terms. When you distribute the b minus a squared in, the numerator becomes b minus a squared times n squared, and on the denominator we have 2 times n squared. Okay, so we just care about the coefficients of the highest degrees, giving us, well, the highest exponents, giving us just b minus a squared over 2 when we take the limit. So we're left with just this. Okay, so I'm skipping a lot of steps here. You can work it out and write it out properly, but for now this is the answer that we get. Notice that both terms have a b minus a. We could factor out a b minus a, leaving us with a. If we factor out a b minus a, we're left with a, plus here we're left with a b minus a, one of them, because there was 2 of them, we took one out, over 2. Okay, so we have to get from this to this. We want b squared minus a squared, all that over 2. How do we do that? Find the common denominator, because you're adding fractions. So this we could think of it as 2a over 2, multiplying the top and the bottom by 2. And now we add the top since the bases are the same, giving us b minus a. Let's put a square bracket. 2a minus a is a plus b, all that over 2. Okay. And now we just multiply. So we have the division by 2, so we'll leave the 2 on the bottom. But on top we get b times a, which is ba. B times b is plus b squared. Negative a times a is negative a squared. And negative a times b is negative ab. Notice the ba and the negative ab cancel. Same number, opposite sign. 2 times 3 is the same as 3 times 2, so it doesn't matter that a and b are reversed. So you can think of ba as just positive ab, and that cancels with the negative ab, leaving us with b squared minus a squared over 2, exactly what we wanted. Okay, so this is the proof for this statement over here. Okay, the next thing I want to add is, as a challenge, go ahead and show that the integral from a to b of x squared is equal to b cubed minus a cubed over 3. And as another bonus, let me just erase this, try to solve that d from a to b of x cubed dx, sorry, I forgot to write my dx, is equal to b to the 4 minus 8 to the 4 over 4. So I'm challenging you with this. Use the idea that we just did for B to prove C and D. Prove these two claims, okay? So good luck with the challenge. Again, I hope the video helped, and I hope you have a better understanding of properties of definite integrals, and I'll see you in the next video.